Ever wondered how a computer's many parts work together seamlessly? It's like a massive transportation system, all in perfect sync. Every single thing your computer does, from opening an app to playing a video game, happens because the control unit is orchestrating thousands of tiny electrical signals at lightning speed. The control unit makes sure everything works in perfect harmony. In the early 1940s, the ENIAC, one of the first general-purpose electronic computers, relied entirely on a hardwired control unit. Its control unit was implemented with intricate wiring and switch panels, meaning every operation had to be physically configured by engineers. In 1951, Maurice Wilkes, a British computer scientist, introduced the concept of microprogramming while working on the EDSAC, one of the earliest stored program computers. Wilkes proposed using a control store, essentially a small, programmable memory, to define the instruction set of a computer. This laid the foundation for microprogrammed control units, revolutionizing CPU design and influencing modern computing. So, what's the difference between hardwired and microprogrammed control units, and which one is better? This is what we are going to explore in this video. Imagine a bullet train. It's sleek, efficient, and hits its stop in record time. That's the hardwired control unit. This control unit is pure hardware, a tight-knit crew of components etched in silicon. It kicks off with the instruction register, snagging the CPU's next order and locking it in place. The decoder jumps in, decoding that command into signals. Those signals race to the control logic generator made up of logic gates and flip-flops, firing off electric pulses to drive the CPU's moves. The clock keeps it all in sync, ticking out a rhythm so every step, fetch, decode, execute, hits on time. And then there's the condition code flags, little status checkers tracking things like zero or overflow from the last operation. The key difference between a hardwired control unit and a microprogrammed control unit is how control signals are generated. In a hardwired control unit, the control logic generator takes input signals like the opcode, status flags, and timing signals. Control signals are set by fixed Boolean expressions of these inputs. These expressions decide exactly when each control signal turns on. Once the expressions are set, they're used to build the control circuit with logic gates. However, the main drawback of a hardwired control unit is its lack of flexibility. The same fixed circuitry that makes it fast also makes it difficult to modify. But what if there was a way to make the control unit more flexible? One that didn't require physically altering the processor every time you needed a change. That's where microprogrammed control comes in. We have seen that an instruction can be broken down into phases such as fetch, decode, execute, and write back. Let us take this add instruction as an example and focus on the fetch phase. This single phase can be split into smaller steps. The first step involves moving the instruction address from the program counter to the memory address register, which is a special register in the CPU that holds the address of the memory location that the processor wants to access. Next, the address is placed on the address bus, and a read command is issued. The third step involves reading the instruction into the memory buffer register, which is a special register that acts as a buffer between the CPU and the main memory. This step also simultaneously increments the program counter. The last step involves moving the instruction from the memory buffer register to the instruction register. These smaller steps are called microinstructions, and they are the core of how a microprogrammed control unit works. These microinstructions are stored in a control memory and are arranged in a logical order, forming a microprogram. A microprogram is a structured sequence of microinstructions that control the internal operations of a CPU to execute a specific task, such as moving, adding, subtracting, and memory access. When it comes to control units, RISC processors tend to favor hardwired control, while CISC architectures often use a hybrid of hardwired and microprogrammed control. RISC processors, like ARM and MIPS, are designed with a small, simple instruction set. Since the control logic for these instructions is straightforward, it's more efficient to implement it using a hardwired control unit. On the other hand, CISC processors, like Intel and AMD, support a wide range of complex instructions. Managing these operations purely with hardwired logic would make the control unit too complex. Instead, modern CISC processors use a hybrid approach. Critical, frequently used instructions are implemented with hardwired control, while more complex, less common instructions rely on microprogrammed control. That's it for now. Stay tuned for more bite-sized computing concepts. See you in the next one.